So I was originally going to do my mini course on the 3DA model, but then it turns out that like one of the most interesting things about the 3DA model is that it's dual to the 3DB model, and that there's a mirror symmetry thing. So I could not do any reasonable course where I didn't talk about both. Okay, but 3D mirror symmetry is like maybe like a subject that people like haven't thought so much about. There's like a lot of terminology that I would like need to introduce in order to start talking about it. And rather than like try and like both tell you about 3D mirror symmetry and throw a whole bunch of new terminology at you, I'm going to like throw the terminology at you while just talking about ordinary 2D mirror symmetry. And then like I'll use that to talk about 3D mirror symmetry. So first I just like want to do some reminders. Okay, so the formulation of 2D mirror symmetry that I want to talk about, which maybe is not the one that's the most familiar to mathematicians, is starting out with some sort of 2D n equals 2 comma 2 supersymmetric quantum field theory. So the first thing, so I don't assume that like you know what any of this numerology means. So this 2D is that my field theory is going to like live on like two-dimensional Euclidean space or like two manifolds. And then this n equals 2 comma 2 is some bit of numerology that tells you how much supersymmetry your theory has. So the way in which this works is any field theory like this has an action first of the Poincare Lie algebra. So that's just SO2 semi-direct product R2. But then since it's a supersymmetric field theory, it's actually going to have an action of an extension of this Lie algebra. I'm going to write direct sum here, but really like it's an extension. And this pi here means odd part, make whatever I'm going to write in it odd. And if you think about how, and actually just let me complexify this thing just for ease. So if you think about like how, I'll turn it to C2. So if you think about how SO2 acts on C2, basically this thing splits into like a +2 eigenspace and a -2 eigenspace. So one of these C's has +2 weight under this SO2, which is really supposed to be the spin group. The other one has weight -2. And then the two spin reps are the weight 1 and weight -1 representations, respectively. And so this 2 comma 2 numerology says that you have your +1 weight representation and your -1 weight representation. I'm going to take 2 copies of each. So this is like what this 2 comma 2 numerology means. And then it turns out that then like the multiplication of like a weight 1 thing with a weight 1 thing to get a weight 2 thing and vice versa is like what gives this thing the structure of a supersymmetric algebra, or sorry, a super Poincare algebra. So now at least you know something about what a physicist means when they write down something like this.
Why does it have weights +or -2, C2?
Because I took like SO2 acting on R2 and complexified it, and this thing is, and when I write this SO2, I'm really thinking of like the spin. So everything gets doubled.
Okay.
So yeah, so if you break up like the ordinary representation of U1 on C after you tensor it with C, you get like something weight 1 and weight -1, but then this is the spin.
Okay.
So everything is doubled.
Okay.
So that's fine.
Thank you.
Yeah, thanks a lot. Okay, so then inside of this thing, there are two very special elements, which I'll call QA and QB. So these things are purely odd. They live inside of this odd part of the supersymmetry algebra. And they are what are called supercharges, and that means that they satisfy the equation that their square, or equivalently their bracket with themselves, is equal to 0. And whenever you have something like this, which is called supercharge, one can write down two different deformations of your quantum field theory. And so one of them is called the 2D-A model, and the other one is called the 2D-B model. And so this one works roughly by looking at the solutions to the equations QA equals 0, because the supersymmetry algebra acts on the TQFT, so it acts on all the fields, and so you can ask, like, what are the solutions to QA equals 0, and similarly you can ask for QB equals 0. And like the way that this works in like very simple examples, so normally I would say that everybody's favorite example of such a thing is the Calabi-Yau sigma model. But since like we're at a workshop on gauged things, I'll instead write down like the gauged linear sigma model. So this is everybody's favorite example, although I won't put in a superpotential if you know what that means. So I have some group acting on some vector space, and this action, this is a symplectic vector space, and this action is Hamiltonian. So this is like my input for my GLSM. And then the space of fields in this theory are like a principal bundle, a connection, and then a certain section of a bundle, plus a bunch of fermions. So this thing is a section of, on whatever my 2 manifold is, of I take my representation and I make the associated bundle, and I just take a section of it, so that's where the sigma lives. And I have a bunch of these things. And if I look at the equation, if I look at the solutions where this QA equals 0, this thing produces the good old vortex equations. So this thing produces for me the solutions of the equation star of FA equals mu composed with sigma, and also del bar of sigma equals 0. And then there was still a bunch of fermions. So these are the symplectic vortex equations. And then there were still like a bunch of fermions in the game. And what it turns out in this A model, it turns out that what these fermions are going to do is that they're going to tell you to take de Rham, build your theory by taking de Rham cohomology of moduli spaces like this. So, I mean, I didn't do enough in order to tell you that, but basically if you did actually write everything down and keep track of the fermions, you would find some extra structure here. And then in the B model, you get something very similar, where now actually just the curvature oh, sorry, there's one other field who isn't important in this twist, but there's one other Lie algebra value field, chi. So he became a fermion in this twist, which is why I didn't get it done before. And then the things that you get is you can combine A and I times phi in order to get a flat connection. So you can write down this combination. And then my equations become that this complex connection has no curvature. And then that the derivative of my section is flat. And then there's one extra term, which it will end up being a stability parameter, which isn't like that important for what I'm going to do. And then if you keep track of the fermions, you learn that you're supposed to take Dolbeault homology of this whole thing. So sorry, I'll rewrite my connection. All right. So this like gives you the common thing that you know of, that like, you know, for A models, you're basically looking de Rham cohomology for some kind of like holomorphic maps. For B models, you're doing like you're doing Dolbeau cohomology of some kind of constant maps. And so usually people don't notice this in the B model because a constant map isn't a very interesting thing.
Yeah, I have are you requiring that V be sort of an SL representation or something? Or, like where, is there no Calabi-Yau condition at this point?
There's no Calabi-Yau condition at this point. So basically, depending on whether I have that sort of a thing, would like tell me like whether my field theory is going to be like framed, or whether it's going to be like, so like you can always define these things if you like equip your two manifolds with framings. And then like being like a Calabi-Yau basically like lets you reduce that to just being an arbitrary oriented manifold. So basically you can get by. Okay, so this is something that like maybe like people like have not seen before. And the reason that I was bringing this thing up is just to introduce like this notation of these super Poincare algebras, this notation of the supercharge, and then this procedure of passing to the zeros of a supercharge. And this is called taking a topological twist, or this procedure. It's called topologically twisting by the supercharge. Okay.
Physics question.
Yeah.
The untwisted theory, is it approximated by the twisted theory? Like in what sense is the twist a deformation of the untwisted?
Yeah, so basically like the way that you should think of this, right, is that this, the fields in this theory are some sort of like a supermanifold. And you know, you can think of that as being like a very, like a Z2 graded like supermanifold. And in these cases, like I'm lifting that Z2 grading to a Z grading. And the way in which I'm deforming is this Q squared condition tells me that I can turn this, that I can basically add a differential to my functions, to my ring of functions, and then I can take the cohomology of that to get something simpler. So like basically like the way that you should think of this is like, you should think of this as being some sort of a, like the fields here as being some kind of a manifold with a DG algebra as like their ring of functions, and you can just like add a differential to that DG algebra and take cohomology to simplify. So, so the technical word for this is like derived stack. Like you can you can deform like these derived stacks. And so physicists had been doing derived stacks, derived algebraic geometry all along without ever inventing this. So that was actually going to be like the very next thing I said. So you can summarize these things. Or the equations of motion in these two field theories, like in the following derived stacks. So I'm not exactly going to explain what a derived stack is, ever. So part of this is one that we've already seen. So in Dan's talk, he talked about the space of gauged maps. So that was like a very good stack. So that gives me everything except for this condition about the curvature. And then I mentioned that there was some fermions that told me to take de Rham cohomology. So there's a certain decoration that you can do, which I'll explain in a second, which is called taking the de Rham stack. And then the other fermions get put together into taking like the -1, what's called the -1 shifted cotangent bundle of this. And on this other side, you can take your curve and de Rham stack it, and then take the V mod G, and then take the -1 shifted cotangent bundle. So let me explain. I'm not going to use this very heavily, but unfortunately, like this is the language in which I'm using to speak. Sorry. And then in both of these cases, this extra term of the equation that I didn't use, this one involving the curvature here, and this one that I didn't write down here, These things can both be implemented like plus a stability parameter or a stability condition. Okay, so quick digression on these de Rham stacks. I probably won't use these that heavily for the rest of this talk, but I do kind of use them. So the idea is that like suppose that like X was a scheme, or was just like a manifold. Actually, let's just say that. X de Rham is the following derived stack. So you take X, and then you just consider it with its ring of functions being the differential forms on X, and then you're with the de Rham differential. And this thing, you don't need to know very much about it. The only things that I'll ever really use are that maps from X de Rham into BG, or into V mod G, or sorry, just into BG, sorry, I guess it's good enough. It's just another word for the moduli space of flat connections. And then I'll use that functions. Well, I've already sort of told you that functions on X de Rham is the de Rham complex. And then the only other thing, which I'll use next time, is that if you look at the space of quasi-coherent sheaves on X de Rham, that's just another way of saying D modules. So if you just remember these facts, that tells you everything that you need to know about this de Rham stack. But if you want to read about them, these things were defined by Simpson in his work on non-abelian Hodge. Okay, but I'm not going to use this today. But or anything on this.
Is X and C the same?
Oh, sorry.
The underlying classical thing is just always X, or like it's going to be map C to B mod G, or when you put the other.
Where? Sorry. Here?
Yeah.
The underlying classical, so if you don't have any of this stuff, this underlying classical thing is just the space that Dan defined in his talk.
No, I mean like after you put the RAM.
Yes, after you, so this one is not actually a manifold, so this like didn't actually apply. So the technical thing that you have to do is you like take this thing and, well, let me just not tell you about it. I'll tell you about it later if you want to know. Okay, so I don't want to spend any more time on these until later. I'll show you more about this as we use it. But the way to learn these things is to like learn how you speak with them, not to try and learn the definition. The definition is completely unhelpful. Okay, so now we've got these two A models and B models that we built out of this 2D n equals 2 comma 2 SUZ Q of T. And the thing that's nice about these is that these are actually both what are called topological field theories. And the reason that you can tell that that's going to be true, I mean, I didn't write these things down for you, is that if you like look inside the Q cohomology of the supersymmetry algebra, you find that actually both of the translations, like in the supersymmetry algebra, get set to 0. So it's not something that that you could verify from what I've told you. But at any time that that's true, then your theory ends up being topological. It tells you that translation doesn't do anything after you pass to Q cohomology. And so then the question is like, what sort of a thing can you do with a TQFT? So these are like mathematical objects. And so they have a certain axiomatization, which is called the Attila-Siegel axioms. So by the Attila-Siegel axioms, an n-dimensional topological quantum field theory is the same thing as a functor, in fact, a symmetric monoidal functor, from the n+1 category of n cobordisms into the n+1, the n category of n cobordisms into the n category of n-1 categories that are C-linear. I said symmetric monoidal, so I need to tell you a monoidal structure. So here, these are monoidal under disjoint union of cobordism, and these are monoidal under C-linear tensor product. So let me try and tell you like what one gets out of this. So from this, you get a whole bunch of.
When you say n category, you mean n1 category, or do you mean the actual n category?
I always mean infinity n.
Infinity n, so not.
Yeah, but I mean, but I really mean, but an n category is good enough for what you want. I know that these probably like aren't familiar. So you get a bunch of invariants, a bunch of manifold invariants. So the first one is if you look at a manifold of the top dimension, it turns out that this thing is going to give you a number. Actually, sorry, I want to write these things horizontally. I'm just going to try and write them vertically, but I'm going to run out of space. You get a number for your top dimensional manifolds. For your codimension 1 manifolds, it turns out that you're going to get a vector space. And then for your codimension 2 manifolds, which is all we've got in the scenario that I have just told you, then you're going to get a DG category, or a C-linear category. And if we were in higher dimension, where you could go to codimension 3, which is as much as we'll ever use, then the thing you get is a C-linear 2 category. So you get a whole bunch of like invariants for every single manifold. And then the point is that these things are functorial under cobordism. So let me write down one example of what this means. So for example, like suppose that like I was in, well, I guess it doesn't matter what dimension I'm in. So there's one particular cobordism that's everyone's favorite, which is the parapants, which is a cobordism between 2 circles and 1 circle. And one could ask, like, what do I get if I were to apply this thing, this functor, to this parapants? And this thing is going to be some sort of linear map, or of the appropriate kind, between whatever invariant I assigned to 2 circles and whatever invariant I assigned to 1 circle. And then because this thing is symmetric monoidal, this thing is the same thing that I would assign to 1 circle, but I tensor product it with itself. So like this thing tells me that whatever I assign to the circle is going to get a multiplication. So this is like an example of like the kind of structure that one gets. But of course, like there are like many other cobordisms between manifolds. What I'm saying is that for every single one, you're going to get some relationship between the 2 invariants. Okay. So this is something that's like a little bit strange, possibly, but this idea is going to like underline like everything that I'm going to do from now on. And so there's one other thing which is called the cobordism hypothesis. So this is actually now a theorem, and the cobordism hypothesis says that you can reconstruct your entire functor z just from what it does to a point. And if you're an expert, like you know that like maybe I had meant this thing to be framed cobordisms, or if I have extra geometric structure, maybe I need a tiny bit more data than this. But roughly, what this thing says is that you can always reconstruct this whole functor just by knowing what it assigns a point to a point. But unfortunately, that's going to be the worst thing. That's going to be the n-1 category. So like that's like the object that's like the least familiar of all, like the most complicated algebraic gadget. But somehow it knows everything. And so like one example, like where you guys already know about this, is basically Consevices' proposal for homological mirror symmetry. which basically says that like the A model, or part of what his proposal says, is that the 2D A model is basically determined entirely by the Hyperkaler category, and the 2D E model is determined entirely by the category of coherent sheaves. So this isn't in my engaged example, it's just in the ordinary example that people are used to. And then there's like a bunch of work like that Costello has done, that like Lurie has done. The most interesting stuff has been recently has been Calderaro and two have basically like constructed like higher genus Gromov-Witten invariants from like the Hyperkaler category. But they sort of prove that you can get the numerical invariance that you assign to like surfaces like from the category. Like if you could actually like look inside the A infinity structure, you can find actually like what these things assign to like higher manifolds, which is like pretty crazy. Okay, so I understand that this is probably making your brains hurt very badly. It makes mine hurt badly too. Yeah, so badly I can't even get my iPad to open anymore, so who knows what's going to happen next. Whatever, I don't need notes to do this time. There we go. All right, so this is like one thing, but I haven't told you what mirror symmetry is in this language, so let me get these blocks.
And it's all about 2 dimensions.
This is all about 2 dimensions, which is not what I want to talk about at all.
3 dimensions.
Correct. But basically, I didn't want to scare you with all of this by doing it at the same, any worse than I already have by doing it in 3 dimensions first. So the 2D mirror symmetry, so this is the one that people normally call mirror symmetry, is basically the following statement. So the first is that there exists an involution, which I'll call sigma 2D, on the Supersymmetry algebra that exchanges QA and QB. So second, this can be extended to an involution on the space of 2D n equals 2 comma 2 theories. So let me call that involution dual, such that your original theory is isomorphic to taking the dual and then twisting the action of the supersymmetry algebra by my involution. So anytime you have like an algebra acting on like a module, and then you have an involution of that algebra, you can make a new module just by twisting the action by the involution. And this is true. So this is what I'm doing with these field theories and this Supersymmetry action. And so this implies the following thing. If you take the A twist of your first theory, then that's isomorphic to the B twist of the dual, and vice versa. And then finally, if you were to apply like the cobordism hypothesis, and you were in the case where you had like an X and an X dual that were, say, dual Calabi-Yaus, then that would give you like the homological, Consevices homological mirror symmetry conjecture, which is that like the Hyperkaler category of X is equal to coherent sheaves on X dual, for example. So this would be like a corollary, like with this statement. But in fact, like this is something stronger because it actually tells me about like the supersymmetric field theories I started with, not just about their topological twists. But like I'm a mathematician, like basically I don't know how to do anything with the full supersymmetric quantum field theory. I can't construct that, but I can do things with the twists. And so this like gives you back like Consevices' proposal. And so like I'm being very ahistorical here. Basically this preceded like this notion of the cobordism hypothesis and these Atiya-Siegel axioms. Like basically these things were meant to axiomatize like what was going on in this case. Okay, so that was 2D mirror symmetry, and I've used a lot of time. But now that we have all this language, now I can tell you about 3D mirror symmetry in a much more concise way.
Is that involution conjectural even?
No, sorry, this is the involution on the theories.
Yeah. Is that conjectural for physicists too? Is there a physicsy description of the?
I would say that it's conjectural. When you say
No,
it's
wait, on theories it's logical, obviously.
well, it is if you define it by this formula.
Yes.
So basically,
There's another theory that's completely topological.
yeah, so basically the interesting bit is that like I could have actually just defined T-dual to be just change the way my supersymmetry algebra acts on T. The place where this gets content is when like you had like a T-dual that had like a different description, and then this thing becomes like this.
And then it's not even conjectural because there's no conjecture.
Yeah, there's no construction. Yeah.
So you don't expect it in general, it would be half construction, I think.
So the part that's automatic is if the theory is conformal. And that was true for the 2D sigma models, and it's true for some 3D theories. So if there's a conformal fixed point, that thing can be described in multiple ways by various gauge theory-ish data. And the conformal fixed point is the thing that has, you might say tautologically, this involution. And it's only interesting insofar as this involution exchanges the different descriptions of the gauge theory data. In 3D, it's not true that all theories are.
But I mean, it could be, if you want to say that this dual theory automatically has a geometric description of T has. I don't know.
Yeah, basically, like, I don't know that you guys have a proposal for what T-hat is.
Right, I'm not sure that's automatic.
Yeah, that's what I'm saying. That's the part. Yeah, so I would say that it's conjectural.
Do you know any examples when T has a Lagrangian description, T dual does not have a Lagrangian description? I think it's possible.
I mean, you know it happens in 3D.
In
Right?
3D, you know, but I'm not asking about 2D, but most probably 2D counts too.
Like, non-abelian mirror symmetry in 2D is so...
Actually, maybe can we table this?
Yeah.
Just so that I can get through some other things. All right. So then now this 3D mirror symmetry is a similar relationship where now I have some new kind of supersymmetric quantum field theory. So again, it has an action of some super Poincare algebra. Again, it has these QA and QB type operators. And one can do this topological twisting procedure. And here, like, we get totally different topological field theories, one of which is called the 3DA model, and one of which is called the 3DB model. So this one goes also by the name of Rosansky-Witten theory. And most of what we're going to do is actually like unpack the details of what these theories are. And this one goes by the name also of like 3D Seiberg-Witten, or maybe 3D Donaldson. Seiberg-Witten maybe is what if I want to throw in another. And so this thing has the following description. So I'm going to tell you, so I told you this one in the gauged case, but I'm going to do that more slowly later. So let me just tell you what happens like when you don't have a group in the game. So in this case, then, like one example of such a theory is called the Hyperkaler sigma model. So here, your fields are the following. I have just some sigma, which is a map from my 3 manifold into some Hyperkaler manifold X, and then I have fermions, which I will never write for you. And when you deform this thing to the 3D A model, this map, so I'll explain this in a lot of detail in a second, but this map becomes a spinner, and then your equation is actually that the Dirac operator of your spinner actually vanishes. But this has another nice description when you are, since you're in 3D, you can describe your spinners in terms of quaternions. And so if I had a framing on my manifold, this is the same thing as saying that I ddx plus j ddy plus k ddz of sigma is equal to 0. And so this special equation, which is the ungauged version of this thing is called a Futter map. So you notice that this thing is like a quaternionic version of the holomorphic map equation. Basically, now I've got 3 complex structures instead of just 1. And you can always factor this thing. Maybe I'll write it in one other way, just so that we can, just because it's sometimes helpful. So another way that you can write this thing.
Sorry, what was that first equation? Just the top D.
This is just the Dirac equation. This is the 3D Dirac operator.
So is that supposed to be equal to 0?
Yeah, that's 0, and this thing can also be rewritten in terms of the quaternions.
Oh, I see.
And then what I'm saying is you can also write it in one other way, which is sometimes kind of nice. So if you had a splitting of your 3 manifold into an R times C, like a real thing times a complex thing, then you can also write this thing as del bar of sigma is equal to minus j times d sigma dt. And so then you see that if I had a solution that was time independent, then this thing would just be a holomorphic map. So basically I'm just pulling k out of here and then relabeling x, y, and z in order to get to this description. But these things are called Futter maps. And then this Rosansky-Witten one, this one actually continues to look in the same way. This one, or as this one down here. So this one is actually just a constant map. And again, just like in the last thing, there were fermions that told me I was taking Bilbao cohomology here. So this theory is going to be something about algebraic geometry. And on this one, I'm taking Duram cohomology. Okay, so this was sort of like a crash course. Let me say the last thing about it. And then exactly like in the 2D case, there's going to be this 3D mirror symmetry involution, which I'll write with an exclamation point. And it exchanges the A and B models of mirror theories, just like in the 2D case. And then if one were to apply this Atiyah-Siegel axiomatization and the cobordism hypothesis, you would see that the thing that you would most like to prove about this is that there's some 2 category that I can build out of the Seiberg-Witten equations and some 2 category that I can build out of the Rosansky-Witten equations, and that these two categories get exchanged by 3D mirror symmetry. So that would be the fanciest thing that one could prove. That would be Consevices, the version of Consevices homological mirror symmetry conjecture. And I guess what I'd like to explain by the time this week is done is something about actually what we know about how to do that.
So you assume X to be compact?
I did not.
But then these axioms, don't they imply that
Yeah, they do. That something's finite dimensional. Yeah, but you can always work over the center. There's ways of getting around, or there's slight modifications I can use. I'm gonna put in mass parameters and stuff to make it finite later. Anyway, so basically there are some small lies I told that I've been caught in. Okay, so let's see. How much more time do I have?
10 minutes.
Okay, that should be enough. Okay, so what I'm going to do now is I'm going to try and more carefully tell you what the equations are for the 3D A model and B model, since we'll be using it like in a lot of detail. Like I don't think that this was really sufficient. But this is just sort of, that was just sort of to like orient you as to like what sort of a thing like one should expect. And I promise that vortices will appear. Okay, so the one that I want to talk about is the gauged Hyperkaler sigma model. So I just told you about the Hyperkaler sigma model before. The reason why this one's going to be so interesting is that unlike in the 2D case, like in 2D mirror symmetry, we have a lot of examples of like manifolds being mirrored to other manifolds. Like for Claudian manifolds, that's true. But basically in 3D mirror symmetry, like that almost never happens. Like the space of manifolds does not like behave well under this involution. But fortunately, like gauged sigma models like do behave well. So it's basically much better. And I think that we like only really know, I think we know the gauge things a lot better. Okay, so the input for this gauge Hyperkaler sigma model, well, one thing is going to be a Hyperkaler manifold. And then the second thing is that I'm going to want to have an action of G times the unit quaternion, the group of unit quaternions, SP1. So this thing is also isomorphic to spin 3. And there's going to be a lot of copies of the unit quaternions showing up, and they're all going to have different roles, like in this game. So I actually want to give this particular copy of SP1 a name, and so I'm just giving it a subscript. Okay, so I need to have an action of this G times SP1.
What does H stand for?
Higgs. And the thing that I need out of G is that I actually need this thing to be a hyper-Hamiltonian action. So that means that this thing's got 3 symplectic forms. It's got an I symplectic form, a J symplectic form, and a K symplectic form. Really, it's got a P's one's worth, but at least it's got those 3. And I need this thing to be Hamiltonian for each of them. So that means that I have a moment map for each of these sorts of things. And these things, well, in a second, I'll tell you, so there's 3 of them. The imaginary quaternions are 3 dimensions. It's not that weird that I could write it this way. So basically, this has like an I component, a J component, and a K component, and I told you those were the 3 moment maps here. And then this action, so this one has to be hyper-Hamiltonian. And then this one has to be what's called permuting. And so what that means is that it induces the standard action of SP1 on S2 on the twistor sphere, S2. So this is the space of complex structures on X. It's like A0 times I plus A1 times J plus A2 times K. And then in order to be a complex structure, all these things have to, the norm of A has to be equal to 1. So there's a space, there's a sphere's worth of complex structures on X. And basically this thing acts on X, therefore it acts on the space of complex structures on X, and I want this to be the standard action of SO3, of spin 3 on SO2. Or think of on S2, where I think of this S2 as sitting inside of S3. So that's what I mean by like a permuting action. Okay, so that's good. And then because that thing's permuting, that means it permuted the complex structures. That means it has to permute the moment maps. So I want this copy of the imaginary quaternions to transform under this copy of the unit quaternion, acting by conjugation. Right? So conjugation preserves the real quaternions, and so I can take the complement. All right, so then this thing has the following bosonic fields.
Can you just say an example of such a thing? Vector space?
Yeah, that'd be the best one. Yeah, HN with its standard action of the uniquaternions is the main one. And that's really the only example you need to know in order to do everything that we want to do. And actually, it's like kind of hard to find permuting actions.
Can you give another example?
Most of the ones I can give are singular, or like singular hyperkalers. You could say something like the nilpotent cone minus the origin, like of SL2 minus the origin or something.
And you would want to apply the theory to that?
I probably would not. That one's going to arise actually as a quotient, and I just removed the singular part to make it work. I don't have any other examples that I like other than that, but other people are more brave than I. Okay, so my fields are basically a principal G bundle on my 3 manifold, the convection 1 form. A, living inside of 1 forms on the 3 valued in the adjoint bundle. So this is my notation for the associated bundle. And then I have my hypermultiplet scalar. Which is, I will not call sigma because Tudor wanted to use sigma for something else. Sigma model. And then there's a vector multiplet scalar. Which is going to be valued in the adjoint bundle. Or sorry, not the adjoint bundle, sorry. The trivial G bundle associated to G, and then I'm going to tensor this thing with a copy of the imaginary quaternions. And this is a totally different copy of the quaternions that I'm going to mark by C. This thing has an action of SP1C. So it's just another copy of SP1, but it's a different copy. Okay, and then there are 2 parameters for this theory, but I'm running out of time, so I'm not going to write them. Trying to figure out how to get here in the least amount of time. So let me just tell you one thing about the supersymmetry algebra. So it's a copy, yet another copy of SP1. This one I'm going to call E because it's supposed to be the Euclidean group. So I told you that SP1 is spin 3. And then this is going to be the complexified superfunctory algebra again. And so now my quaternion, or my odd things are the following. It's going to be a copy of C2 that transforms into C representation under SP1C, tensor 1 that transforms under H, tensor 1 that transforms under the Euclidean group. And then this thing has an action of SP1C times SP1H, basically acting on these 2 guys. And the way that it's acting is each of these things has a symplectic, oops, sorry, that should be a tensor. Each of these things has a symplectic form, so their tensor product has a Riemannian metric. And so I'm using the identification of this thing with the spin group of C2C, tensor C2H with respect to that. So basically spin 3 times spin 3 4. Okay, and then to twist, I need the following data. So I need, as I said, I need this Q, which is a supercharge. So it's an odd thing that squares to 0. And then I need the following other thing. So I'm going to need commuting commuting actions of the following, or commuting maps of the following form. So I'm going to need yet another copy of SP1, which is going to be my modified Euclidean group. And that needs to embed into SP1E times SP1C times SP1H. And the thing that this has to satisfy is that in order to twist, I want to use this Q as a differential, which means it has to transform it as a scalar under my Euclidean group, but this thing is transforming as a spinor. And so I need to like redefine my fields in order to make that thing a scalar, so I need Q to be a scalar under SP1 prime. And then the other piece I need is I need a U1 inside of this same, just this part, SP1C times SP1H. And I want this to use this thing as a differential, and this U1 is going to be my cohomological grading, it turns out. And so I need Q to have weight 1 for this action. So because differentials have weight 1. This thing is going to be my cohomological grading. Okay. All right. So I can almost finish this up. I need about two more boards. But there'll be some PDEs on both of these boards, so you'll like it. Okay, so the first one, so there are two classes of these things. So the first one gives rise to the A model. So that's when this SP1E includes via as the diagonal into spin 1E times spin 1H. And then my U1 is going to just be some maximal torus inside of SP1C. And so this thing is going to determine a complex structure. On the quaternions that I've marked by C. Okay, so then what does this thing do? Okay, so now I need to choose a spin structure. Q, say, some spin bundle.
It's SP, not spin.
These are SPs, sorry. Thank you. There are also spins, but not spin ones. Yeah. Okay, so, all right, so now I'm going to go ahead and redefine my fields using this SP1 E prime. And so what does that do? So I go back and I look at my original fields and I say, like, which one of these things actually transform over under SP1H? So X does, and yeah, so mainly X does. So what happens is that my S is now no longer a scalar. Now X is going to get turned into a spinor, so he's going to transform both under SP1E and SP1H. And so now I can take my X and I can twist him by Q times P. So because he has now an action of SP1 Euclidean prime and the action by G. So I can like take the associated bundle and take a section of that. And then this makes the following thing happen. So also I can compose this guy with the moment. And now this thing used to be a scalar, and now it's actually going to turn into a one. Track everything. And then finally, the complex structure. This thing splits this field I was calling phi into a sigma and a phi under the splitting of the imaginary quaternions for C is basically going to break into C under this U1. Okay, and so now I can write down my equations. And so my equations are that the Dirac equation for S should hold, plus I can act on S with sigma. And then the more interesting equation is that the Hodge star of FA plus the action on sigma plus my moment map should be equal to 0. So this thing looks a lot like the symplectic vortex, like kind of looks like it's kind of symplectic vortexy. And then this other bit is Bogel-Monod E. And then I'll keep this around. If you pay attention, this phi transforms under the U1 that I said is my cohomological gradient. So phi is actually going to turn into a fermion now, so I shouldn't even be writing down its equations if I accept what the conventions have been doing. But I'll do it anyway. Or sorry, it's not going to be a field of cohomological degree 0. Basically, I told you that I was going to be taking de Rham cohomology of these moduli spaces. It turns out this thing will turn into the equivariant parameter in that cohomology. But anyway, it'll satisfy some random equations. These aren't very important. Just a bunch of commutators are 0. So that's the A twist. And then I can do the B twist.
So these are the generalized Seiberg-Witten that you advertise in your...
Yeah, so these are these generalized Seiberg-Witten equations. So yeah, let me actually say like a couple of things about them. So like if I had no group, then it's just the Dirac equation or the Futter equation. If I had no S and no sigma and no phi, so let's say that I had no X. So say X was a point and then I set sigma to 0. Then these things are actually turning into the Bogel-Monod equations. Like just this bit here is the Bogel-Monod equation. Yeah, and so that's maybe like the two most important specializations. And then I told you that if I had this way of rewriting this equation in terms of del bar, if I could split my 3-manifold into an n times C, then I could rewrite my Dirac equation this way, and if it was time independent, that tells you that it's holomorphic. And so if I did the same thing, this thing will turn into a vortex equation, like if I look at time independent things. So that's like maybe. Can I just say the B ones? Like it'll only take 1 second. I won't go through the whole procedure, but it'll only take 1 second. So the B equations are actually very easy. So the B equations are just the following. So this phi basically becomes now a 1 form valued in G, and so I can make a connection A plus I phi. And then my equations become that the curvature of this is 0, that my section is flat, and then there's one last term, which is 0. Star dA star phi plus the real moment map. 0. Oh, sorry. And then the last one is that my complex moment map is 0. So these become the equations. So let me just say what these things mean. So this thing now is a complex connection. I'm asking for it to be flat, and then I'm asking for my section to be flat, and then I'm asking for the complex. Now I have a part of what I had when I choose the U1 and SP1H is a complex structure on my Higgs branch, and so I can break my moment map up into a complex part and ask for that to vanish. So this thing is just the way that I was writing it, it's a map from M3 de Rham into the Hamiltonian reduction, or into the complex symplectic reduction. So that's it. Okay, so now you know the equations.
Let's thank our speaker.